Good afternoon. This is CIVE 638, and I'm Professor Ponce from San Diego State University, Department of Civil Engineering. And today's class is 072, which is the 7th week, the second class. Today is a Thursday. We teach this class twice a week. And the subject today is more on the geomorphology. Particularly, we're going to be talking today or covering the lane relation, the famous lane relation. It's one of the most important concepts in our class. Today, I'm going to cover from C17 till C22, hopefully. So let's get started here. The first one is actually a summary. It's a 20-page summary of my doctoral dissertation. I'm not going to go into detail because this is a very complex subject, you can imagine. But at any rate, I'm just going to show you what we did so that you can see in some ways where Professor Ponce is coming from. You know, what did we do early when I was at Colorado State in the middle 70s. For 3 years, I went to PhD school. And this work is what we did, or I did, the last year of those 3. Because usually you go 3 years, and then after the second year, then you qualify to do the thesis and take the exam. And that's the way it was. By the way, Colorado State University at the time was one of the, if not, I think it was definitely, the largest civil engineering hydraulics school in the world. I think I could say that. Because I believe at the time I graduated, which was 1976, they were graduating from 40 to 50 doctoral PhDs. It's a heck of a lot. Most very good schools graduate 5, okay? 5 or 10 maximum. And here, and why were they doing that? Because, I don't know, that's just the way it happened. Everybody wanted to go out there. Fort Collins was a nice place to be and so forth. And Colorado, you know. And at any rate, so that's the story of the Colorado State University hydraulics program. And among the water programs at Colorado State, there were 7 water programs: hydraulics, hydrology, water resources, etc. And the hydraulics programs was led by Professor Simons, who was the head of the whole thing. The head of the building was Daryl Simons. And I, again, signed up under him. At the time, he had maybe 10 to 15 students, PhD students. Some of them were masters, actually, masters and PhD students, 10 to 15, it varied. So we did this research with Khalid Mahmoud. Like I told you earlier, I'm not going to specifically talk too much about it, but I want you to get the gist of what we did. What did we do? We did a generalized 2-dimensional linear stability analysis of the flow of water and sediment in the subcritical range is presented, meaning we were going to do some dynamics here, perturbation, modes of small perturbations. It's dynamics, okay? Fluid dynamics. We were going to do it in 2-dimensional form, and we were also doing it with water and sediment. So we had to use the collection or the set of 2-dimensional water and sediment equations. Now, for your knowledge, you can solve water in 1-dimensional way, or you can solve water and sediment in 1-dimensional way. And that's done, by the way, by the model, the Army Corps of Engineers model, HEC-RAS, but that's 1-dimensional. I should also tell you that at this point for about 10 years, no, actually more like 20 years, the RAS model, the River Analysis System model, has already been able to do 2-dimensional. So, but the 2D of HEC-RAS is a mathematical model of the equations. In here, we're going to be doing something different. We're going to be looking at modes of perturbations. Our interest is to develop, or rather to come up with the predominant wavelengths of the meanders, because these channels that we were looking at were meandering, and we wanted to see what were the predominant wavelength of the meanders. So we used a methodology that had been developed by a gentleman out of Australia, Dr. Callender. he had done earlier work. But in true fashion of all very good researchers, he didn't complete the work. Remember, I think I said that. If I didn't say it here, I must have said it in the other class. But Professor Yevevich, who was one of my mentors, one day got me on the cafeteria and said, Ponce, I wanted to give you some secrets. Don't forget that at the time I was 30 years old and he was 60. So the situation was reversed. So Yevevich told me, he said, a very good researcher never completes the work. I said, what? I couldn't understand what he was referring to. He says, yeah, because if you complete the work, then nobody can follow you. They can't do anything else. What you should do is do half of the work and then leave the other half for somebody else to finish it. And that's exactly what Callender did. Whether he knew it or not, that's what he did. Because once we read the paper by Callender, we said, meaning I said, Skyhead didn't complete the work. The method is great, but it's not complete. It can be completed. So we did that. Spend about a year doing this. Well, a year, including the travel that we did in, we went all the way to Pakistan in order to gather the data to verify the model. So that's the gist of the elements in here. I'm going to skip over. I'm just going to show the equations. These are the equations: momentum equation, momentum in the x direction, momentum in the y direction, flow continuity, and sediment continuity. And these are the equations that we worked on in connection with this study. In addition to these equations, we had to come up with some additional equations for resistance and transport. And I'm not going to talk too much about that because I'll be talking about that in the next paper. So let me just say that we need to develop the resistance and transport functions. And finally, at the end, we came up with a formula like this, which describes the celerity. This is for the celerity, and this is for celerity over here, celerity in the ordinates on the right, and the beta, which is the amplification factor of the small perturbations. And the beta came about 6 or 7, actually 5 or 6, somewhere in that range. That means that the ratio of the width of the length of the wave to the width of the channel was going to be 5 or 6. And the celerity. Celerity was an interesting concept because celerity is the velocity of the wave. And we were talking about the bed wave, not the wave like you would imagine a water wave. No, this is not a water wave. This is a sediment wave. It's a bed wave. But the calculation allows you to, at the same time you get the celerity, you can also get the amplification. Amplification or attenuation. In this case, it was amplification. So this is basically the finding, the main finding of the, and the thing that we did that Callender didn't do was that we non-dimensionalized the entire procedure. He didn't do that. And I think I mentioned this before. I said it's better to do the non-dimensional or dimensionless analysis because then you solve all the problems. If you don't do that, you solve some problems, but not all of them. So we did that. We put it in non-dimensional analysis. And by the way, I should tell you that by doing this work, this qualified me tremendously to do the next step of the work, which was not included in my dissertation, but it had to be done. That was the so-called famous S-curve that I must have mentioned in this class. Those of you that took computational hydraulics with me last year must remember some of what I said. The S-curve, I call that my highest accomplishment, I believe. That's what I think. Not everybody else thinks that. According to the populace out there, my highest accomplishment is my paper on the curve number, the one that I've discussed in hydrology. That paper has about 1,300 citations, while my S-curve only has about 600 or 700. My S-curve is in position number 4 or 5. Well, the curve number, why is that? Because the curve number was a review paper, meaning everybody reads it and they comment, and the review papers get a lot more readership than just a technical paper that is trying to advance knowledge, which was the case of the S-curve. Okay, so finally at this point, we spent 3 months out there in the boonies. Actually, it was not in the boonies. I was 2 months. There was 2 months in the city or the town, and then eventually I had to go to this place, which is very far from everywhere. It's Western Pakistan. But let's not forget that that was in When was it? No, it was in 76. At this time, I wouldn't go there because it would be risking my life to get out there, you know, foreigner, etc. Doesn't know the language and so forth. But at that time, it was pretty peaceful. And so I spent 3 months out there. I spent about a month at the QB link, a month at TP link, and another month at CJ link. These are the link canals which we studied, and they have different hydraulic characteristics and therefore different responses. As you can see, the response over here is here, right in here is a little bit more here, and so forth. These channels are more or less the same, but not exactly the same. So it is understandable that they have different results. We had a lot of fun doing this, by the way. And the reason for it is because I had trained to do this, and we took the classes that underpin the knowledge and so forth. And right after we finished that, we were just, we thought that we could solve any kind of these problems because we had the, how can I say, confidence that we could do it. And then we proceeded to do the S-curve. And finally, I just said that, that we covered the 3 channels, not right. Now, what I'm going to do now is I'm going to go and discuss the Indus Basin irrigation system, because I already mentioned the QP, the TP, and these channels, and of course they at this point don't mean anything to you. So I am going to discuss briefly the Indus Basin irrigation system. This system was built in the 50s and 60s. When I went there in 1976, it was already built. They had 12 canals. How big were they? The Chas Magellan was the biggest one. This one over here, it says Chas Magellan, which I participated also. I actually worked on the QB, which Quadratic Baloki, the CJ, Chas Magellan, and the TP, which is the Ponce Punjab. These are locations in Pakistan. Okay, so I first was over here somewhere, then over here, and then over here. These channels are about 70 miles. At this point, I'm not sure if it's miles or kilometers. I think it's miles, because in Pakistan, they use that, the American, the US system. Miles, the widths vary between 200 and 300 feet. 300, actually, the Chas Magellan was 380. I remember that right now, very clearly, even though it's been almost 50 years since I did this study. 380 because it was the widest of all of them, 380 feet. Very big channel. Were these channels natural? No, they were entirely artificial. 12 channels in an irrigation system in one country, that is extremely unusual. Why would the Pakistani want to do this or need to do this more than anything else? Where? Well, you gotta go back. You gotta go back and examine the politics of the situation. In 1947, the Indian subcontinent, meaning India and Pakistan, achieved independence from Britain. Because prior to that, they were under Britain, under the domain or the rule, I guess you could say rule, of the United Kingdom. And then in 1947, they achieved independence. And since there was a lot of people, there were 2 religions out there, the Hindu religion and its variations, it's got a lot of variations. And then the Muslim, and the Pakistanis were mostly Muslim, and the Indians were Hindu. So they agreed they couldn't form one country, so because of the religion. So they decided to form 2 countries, and the Pakistanis on the west were named Pakistan, and then India. Okay, but the problem was the hydraulics and the hydrology. The Indians were taking the headwaters. The Indians were here in control of the headwaters of the Ravi River and the Sutlej River. Okay, and look at this. This is India over here, and this is Pakistan over here. That's the division, the limit between these 2 countries. So the Indians, I'm not going to say they were mad at the Pakistanis, but they were not in friendly terms. So they decided to take the headwaters. Basically, they took all the water. This is India here. okay? And this is Pakistan. So they took all the water from these three rivers, the Chenab, the Ravi, and the Sutlej, particularly the Ravi and the Sutlej, meaning that the water was flowing from these two rivers into Pakistan was nothing. It was not there. They took it all. Now, the Pakistanis developed this area, well, over centuries, right? But they found themselves toward the end of the 1940, 50, without enough water over here in this area, because the water had been cut at the headwaters. So that I'm sure I wasn't there. This happened in the early 50s, late 40s and early 50s. I certainly wasn't there. I was a young man at that time, going to grade school, right? So obviously I didn't even have the slightest idea that 20 years later, I was going to be doing this work. But at any rate, the Pakistanis decided, with the help of the international community, US, UK, and Europe, to build these canals and transfer the water from the west, where they had the water. There was enough water in the Indus. So the idea was to move the water from the Indus into the Chenab, and from the Chenab onto the Jhelum, I'm sorry. Indus to Jhelum, Jhelum to Chenab, Chenab to Ravi. So you can see these rivers are, or rather, these channels are connected in that way. Plus, it's not just the channels. You got to have intakes and so forth. It's a very complex, extremely expensive for the time hydraulic project. I believe it could be regarded as one of the largest hydraulic projects. I'm not sure if in terms of money spent, but you could Google and find out. You know, Google is telling us 98% of everything right now. Google link canals of Pakistan, link for link, because these canals are supposed to link. So you Google link canals and you get there. Okay, and they're going to show you, they're going to say 12 canals, and these are the canals, and so on and so forth. Okay, so that's the story. So it was political solution, rather a technical solution to a political problem. Had there been no partition, they would not have needed, they would not need to do the canals. But unfortunately, there was partition. It doesn't tell the story of East Pakistan, which eventually became Bangladesh, by the way. But that's another story, which has nothing to do with the hydraulics or the sedimentation, so I'm not going to talk about it. So at this point, I am going to go back in here, and now I'm going to go to the paper by Lane. Who is Emery W. Lane? He lists himself as consulting civil engineer over here. Let's take a look. This is interesting. He lists himself, when he wrote this paper, as consulting hydraulic engineer in Fort Collins, Colorado. That's where my alma mater is, in Fort Collins. So I'm assuming, because I don't know everything, that at the time he was a consulting engineer. It must have been, I'm guessing here, wildly guessing, that by that time he was old already. He had been around a long time. So he taught for sure at Colorado State, maybe the 40s and 50s. And then after that, he retired. And in 55, he wrote this paper. So that's why he lists himself as consulting hydraulic engineer in Fort Collins, because I figured he probably retired from teaching, and then he wasn't moving. He stayed in Fort Collins. Nice place to live anyway. Okay, so Fort Collins. What is Fort Collins? Fort Collins is what Colorado State University is. And why there? Why turned out that huge, the small place, unimportant to everybody that at the time, you know, Fort Collins was a very small town. When I moved into Fort Collins, I believe in the year 68? Yeah, 68, it had about 30 or 40,000 people. Very small town. Later it grew and became very important. But the point is, why there? And the answer is, I believe the proximity to the headquarters of the Bureau of Reclamation in Denver facilitated the meeting or the agglomeration of people that knew hydraulics in the area, both in Denver as well as in Colorado Springs and Fort Collins. And I wasn't there, like I said, but Fort Collins started to get important in the late 40s and early 50s, and by the 60s, they had already grown and become extremely important in terms of the water hydraulic programs, hydraulic graduate programs in the US, and why not say it, in the world. The population, the graduate student population at Colorado State when I was there was largely foreign from all parts of the world. my guess would be 70 to 80%, okay, from all parts of the world. So they basically educated myself and many others that went on to do hydraulics all over the world. We've been doing this for 50 years now. So this is Emory W. Lane. And like I said, he was my academic grandfather, but because I know that Darrell Simons was his student, because Simons mentioned Lane in class. We, of course, had never met Lane. I've seen pictures of the gentleman, but no, have not met him personally. But Darrell Simons used to talk about him. So this is the story, or rather the paper that Emory W. Lane wrote in 1955. I'm only going to read the first part because I think it's important. The rest becomes really entangled into all his ideas, which is good, but I'm going to have you read that, not me. Morphology. I'm talking about morphology for this is the second week that we're talking about morphology. The form, the science of structure or form. Fluvial, defined as is produced by the action of flowing water. So flowing water is going to form its own river. And then the river is going to be studied by geomorphologists and engineers, typically civil engineers. It is also, by the way, studied by geographers. So there's three professions, so to speak, that have a claim on the issue of fluvial geomorphology and geomorphology in general. And those three are the geomorphologists, which are geologists by training, by the way, the geographers, which I don't know, I'm not going to talk about geography, I don't know anything about it, and civil engineering, which we are civil engineers. Okay, so those three have a stake on the issue of fluvial morphology. There are interactions. I should admit, there's interactions. Typically, the engineers are more analytic, and they have a tendency to put more numbers and equations into anything, while the geomorphologists are less analytic, and the geographers are hardly analytic. So that's the way the division is, okay? And I happen to know because when I was there as a student, Darrell Simons had a pal in the geology department who was a geomorphologist, and his name was Stan Shum, which was famous. Stan, in his career, which spanned about 40, 50 years, he wrote about 15 books on geomorphology. I know what it takes to write a book. I wrote 6 or 7. So I know he doubled me. He wrote 15 books on the subject of fluvial geomorphology. And I should mention to you, in case you're interested, that that Stan Shum was on my graduate committee. So he was there when I passed the exam. He's a gentleman, very good gentleman, nice gentleman also. At any rate, enough for Stan Shum, but the issue is Emory W. Lane. Fluvial geomorphology or fluvial morphology is particularly important to the hydraulic engineer. What he's trying to do is to bring into hydraulic engineering a lot of the supposedly concepts that had been developed by the fluvial geomorphologists, okay? Because of many of his greatest problems arise because of the form of streams brought about by the transportation and deposition of sediment. There is an overlap between these two sciences, but like I already told you, the definitions are very clear. The geomorphologists are usually qualitative, while the hydraulic engineers are quantitative. This does not justify the preference for hydraulic engineers, by the way, but I am a hydraulic engineer, so I'm biased a little bit towards quantification rather than qualification. But I do believe at this point, I wasn't born yesterday, that both ideas or both approaches have their rationale and their use, by the way. I should tell you that recently I had a good experience with a couple of geomorphologists from Holland working out of England. They were Dutch, and they're writing a very important paper that a journal of geomorphology has charged them with doing. And in the process of doing that, they discovered that Professor Ponce has written extensively about the Veternikov number. And they realized at the time, or they were convinced, that they could not write that paper without expounding on the Veternikov number. And since that subject is new, they called me up and they had me review the draft of the paper. And we did that in 3 sessions. We had to do 3 2-hour sessions. This was done in January or February of this year. And I gladly, of course, participated. I don't want them to make a mistake. And they could, because they're geomorphologists, they're not engineers. So by the time it gets to be a little bit analytic, then they kind of throw the towel, that's the way it is. And they told me that, by the way, specifically they told me that. They also said to me, interestingly, and this is interesting for you too, that they wanted to make their paper readable to the geomorphologists. And they realized that if they threw too many equations into the paper, it was going to backfire. So that's really cool as a comment. But at any rate, so Lane was an engineer, but he found himself practicing geomorphology. So he wanted to bring all these geomorphological concepts to the engineering field. So he basically in here talks about the geomorphology. I hope I have done the right thing in here. Let me see. No, I did not. I didn't do it. So we're going to have to go back in here. Where am I? Okay, here we go. So at any rate, I'm not going to go into the discussion of what he originates from the studies of Davis, which is the father of American or geomorphology, Mr. Davis, or I don't know if he was Dr. Davis, but he's a very well-known guy. Basically, the geomorphology of the world has to do as a result of the action of tectonism, which brings the rocks up, and erosion, which brings the rocks down. And that's the story. Everything else derived from that concept. Why is there tectonism? Because the surface of the interior of the earth is molten lava and is moving around. The crust is about 70 kilometers. The crust, hard crust, but below the 70 to 100 kilometers, it's fluid, right? So there's going to be earthquakes, there's going to be tectonism and so on and so forth. And we're going to have to live with that. And we are, as a matter of fact, live or die with that. You know what I'm talking about. So, so he finishes up his paper over here, and he's talking about erosion, finite equilibrium grade. And like I said, I want you to read this entire paper. You should, for your education. It is not easy to read, by the way. And he has a couple of examples, and this is a very classical and very well publicized example. This is the degradation below Fort Summer Dam on the Pecos River in New Mexico. This must have been one of his foremost experiences of Lane. I'm not sure if this gentleman there is Lane. I don't think so. But the point is that what Lane is saying in his paper is that this is the amount of degradation downstream of the dam. Because by that time, we already knew that if we put a dam anywhere for the purpose of holding water, we're also going to hold the sediment, and therefore the water downstream, flowing downstream past the dam, will become hungry for sediment. Why? Because water has a property. It wants to take up a certain amount of sediment. And if you don't give it to it, it will take it from the surroundings. No questions asked. It will take it. It will take it either from the bottom or from the banks. If it takes it from the banks, it will be wide. It will erode, it will widen its channel. If it takes it from the bottom, it'll deepen its channel. But no matter what, it will revert back to the transportation of the so-called sediment load that was examined in detail by Einstein in the year 1950. Einstein, 1950, this gentleman, 1955. They probably didn't know each other at the time. I don't think so. Einstein was working out there, California. This guy was in Colorado. I don't really know, to be honest with you. I wouldn't venture even a guess. But the point is, the Einstein paper is dated 1950, and this paper by Lane is dated 1955. So this is a very famous paper that I have actually taken up in my book, as a matter of fact. And over here, I don't know this one. I'm not going to comment on this one. So let me say that is what I would like to say in terms of the paper by Lane. I do want you to read it, by the way. I do want you to read it. It's labeled bold, so you must read it. Trying to extract the truisms that he is talking about. Okay, so then the next paper or the next thing that we're going to read is the Lane principle. We're kind of going, no, we're fine. The Lane principle. So what is the Lane principle? Lane is Emory W. Lane. Okay, so this is my writing. This is what I call a legacy tale. Why legacy tale? That sounds like a fancy term. Well, in the year 2002, after I had established myself online, because I started this project, it's a project because it never ends, in 1999, and 3 years later, 3 years later, I started telling tales. But this is not Professor Ponce's tale. Well, they are my tales. But I had so many tales because I'm basically a storyteller. I've been told that by people, okay? So I had so many tales that I started publishing. I started putting them in one place and then publishing once a month. And the situation ran for 10 years. So I have 120 tales that I have published from the year 2002 to 2012. At that point, I ran out of steam. And I said, well, so be it. That's it. 120 is a lot, more than many people have, a lot of people. But then later on, what time's gone by, 10 years, and I've added 10 more. So the last 10 years, I've added one per year. So as you can see, I am running out of time, or steam rather, in terms of telling tales. But what are these tales about? They're mostly technical, by the way. Actually, you know, I should take that back. 50% technical and 50% non-technical, because we have a lot of tales that have nothing to do with technical matters. But this one isn't technical. This is one of the foremost technical tales that we told on the web. So the lane principle. The natural function of rivers is to carry the sediments and dissolved solids to the ocean. Huh? What is this? The natural function of rivers is to carry the sediments and dissolved solids to the ocean. That's exactly what Mother Nature decided from the beginning. I am going to erode, and I'm going to carry, and I have the rivers to carry it for me, said Mother Nature. And not only were the rivers responsible for carrying the sediment, which is what you could see. They're not microscopic. You could see the sediment, sand, silt, clay. Even clay could be seen. But there's also dissolved solids in microscopic size, molecules. Those cannot be seen, but they still have to be transported. That's the salt. Part of it is the salt. The salt, the components of salt are sodium chloride and the other salt. There's few salts out there very well recognized. Among them, the most well-known is sodium chloride, of course, which is common salt, table salt. So the dissolved solids need to be transported. Look at what I say in here. Humans interfere with this function as they utilize the water resources of the earth, often without realizing that the water is already committed by nature as a carrier of sediments to their ultimate destination. Meaning we shouldn't mess with it, but we should, by the way. No, I'm sorry, we shouldn't mess with it, but we are. Why are we messing with the sediment? Because we need to. There's no other way out. We have to have the water. Why? Because people live in the dry areas. People don't live in the wet areas. Case in point, California. If you go above San Francisco, hardly anybody lives out there. And that's where all the rain is. There's a place in the north and northwest corner of, it's a triangle in the state of California where it rains about 80 inches, I believe, right? 80 inches. It's a lot, or more even. It's a lot of water. And it has the tallest trees, the tallest, the tallest, 80 meters, 250 feet. And in volume also, because if you have an 80-meter tree, it's likely that it's very, very big, right? So we're talking about the redwoods and stuff like that you're already well known, you're already familiar with that. So we have to do it. We've got to do the hydraulics. I grew up when I realized that my profession, the hydraulics, is to move the water from here to there. That's dumb that I should say it, but that's the way it is. We need to realize that our job is to move the water. But then the question is why? And the answer is because society needs you to move the water, and they have to find somebody to do it. Somebody that will study 20 years just to move the water. And that's exactly what we did. We, of course, didn't quite realize that if we move the water, we got to move the sediment, we got to move the dissolved solids, and so on and so forth. And the matter gets really complicated, as we know, and you guys are taking this class now, and hopefully you will follow suit later on with applying these concepts that you learned in this class. Now, to help us understand the process, we examined lane principle of fluvial hydraulics. By the way, I made a mistake in here. Importance of fluvial hydraulics. I did not touch on this page. I forgot to touch this page. This is page number 5 or 6, where he puts forth his famous equation, or rather it's not an equation, it's a relation. That's why people don't refer to it as the lane equation. They say the lane relation. So he said in here, right in here, 1955, that if you take the sediment discharge, tons per day or tons per whatever, measure, times the particle diameter. That is proportional to the water discharge times the slope. And he said that these four values, if you establish their equivalence, not their equivalence, but their values, if one of them goes up over here, on the other side, one of them has to go up. Or else, if S goes up, QW has to come down. If QS goes up, S has to go up. If D comes down, QW or D has to come, or S has to come down. He said there was a direct relationship between them. But he didn't venture into the equalization or finding the equation that will make this proportionality an equal. Why? Because I don't think he could do it. He had a lot of practice. He was a practical engineer. He had a lot of experience designing dams and so forth. But I mean, hydraulics is a very broad field. You don't have to know everything. So he didn't do it. He just said there's a relation in here, and he got famous because of the relation. Why? Because it was an unusual relation. And I guess he got a lot of publicity. I don't know exactly why, but he's definitely a good man. He had not just done this. He did a couple of other things that were very important in the field. So he already had a reputation when he did this. So we go in here now. No, I'm not there yet. I'm losing it here. Here we go. Okay, so this is the relation that he developed in 1955. Although qualitative, yes, it's qualitative because it doesn't have an equal in there. This relation is extremely useful in sedimentation engineering because it links together four of its most important variables. Since by definition, sediment concentration, look at this, sediment concentration is QS over QW. That means if you put QS over QW over here and put it to the left side, and you put the D in the denominator of the right side, then you can say safely that the sediment concentration is a function of direct function of the slope to some power to be determined, and inverse function or reciprocal function or inverse function, it's okay, of the diameter to some power B that needs to be determined. And that this is a correct statement, by the way. According to Lane, an increase, decrease in any of these variables would trigger a corresponding change, increase or decrease in one or more of the others until a new equilibrium is established. Mother Nature is always seeking to establish equilibrium. In other words, she's in steady flow. But we come, or nature comes, and impose a non-equilibrium condition. And what does Mother Nature do? She tries to send it back to equilibrium. That's the truth. All of us that really know the subject realize that that is the case. A case in point, Professor Chan. Who is Professor Chan? You've never heard of Professor Chan, or maybe you have. Professor Chan preceded me in teaching this class. I started teaching this class in the year 2012, and Chan taught it for 30 years prior to me. And he retired, I believe, in the year 2010, somewhere. It was a little hiatus in there, but the point is that Chan preceded me in teaching this class at San Diego State. He was there for 30 years. And Chan had a methodology that he called modeling, where was it? It's fluvial. He called it fluvial. The fluvial model, fluvial 11, fluvial 12. And he needed three conditions to model his flow. And he only had two. He had the slope and whatever it was, I don't remember right now, but he had two conditions. So he needed a third one. Without the third one, he could not have solved it. Why? Because he needed to tell you or tell us what was the width of that channel going to be. He could figure out the velocity and he could figure out the depth, and the two conditions that he had, which is basically continuity and momentum, didn't allow him to get to the third one. So he had to come up with a third one. And at that time, nobody had done that kind of work. So he devised a methodology to develop the third relation, the width, how to figure out the width. Interestingly enough, he wouldn't really tell a lot of people how he did it because he obviously wanted to profit from it. Everybody does that. I mean, I'm not blaming him. At any rate, nobody really knew how he was doing the calculation. But one day somebody queried him in the journal, and he was forced to say something, and he did say something. He said something like this. and I'm quoting him loosely. He says, well, what we're doing is we're trying to make sure that we return to equilibrium. We return to equilibrium. That's exactly what I said earlier. That Mother Nature likes you to return to. If you don't do it, she'll do it for you. She'll return to equilibrium. So that was the magic of Professor Chang. He was putting in there, imposing in a condition to return to equilibrium for lack of anything better. But by the way, it was a good condition, because that's what Mother Nature will do no matter what. Okay. Lane's principle is applicable whenever any of the four aforementioned variables is subject to change. For instance, if water is taken out of a river through a diversion, a new equilibrium will establish itself in the downstream river. Likewise, if only sediment is taken out with a sediment retention basin, as we will have ample time to show, the hungry water, quote unquote, flowing downstream of the retention will seek a new equilibrium, usually through additional erosion, either down-cutting or bank caving, depending on local conditions. Thus, geomorphological adjustments are the net result of changes in water and or sediment routing, or sediment discharge rather. And we have a quote on this paper, on the paper by Lane, which I have already referenced. So now we are going to get to the subject, the subject for today, which is the Lane relation revisited by Professor Ponce. We did this in 2015. Why is it that it took us so long to get there? I don't know. I guess the only thing I could say is that we're busy. We're not just doing this, we're doing 3 or 4 things at a time. Hydrology, hydraulics, water resources, and all kinds of other stuff. So, plus we have to have some fun, right? Like everybody else. So the point, or travel, which is the same thing as fun, in my opinion. So we, in the year 2000, no, it's not 15, it's 11. It's in the year 2011. Later we changed the date, but this is dated 11, because it is my practice to put in there the date starting with the year. So in the year 2011, I came up with this. It was an illumination of many of the things that I had been doing or saying for the last 30 years. So this is not something that happened overnight. It just happened all of a sudden because I said, hey, this can be done. I can improve this. Okay, so we're going to talk about how we revised the Lane relation. We call it, very pompous, revisited. They revisited the Lane relation. To be honest with you, I'm not sure if we have done all the credit that perhaps we deserve. It doesn't matter. Time will tell. Meaning the recognition. This article revisits the Lane relation of fluvial hydraulics. Hold on to your seats, because it's going to get rough right now, okay? Lots of equations, and lots of equations that are physically difficult to grasp, okay? Q sub S, solid discharge. QW, liquid discharge. D sub S, mean particle size. S sub S, slope. That's the Lane relation. The new relation is derived from theory and expressed as a dimensionless equation. Here we go, Professor Ponce. I am putting the Lane relation in terms of dimensionless terms, which we have done for 30 years. So it was not too difficult for us to do this, with the particle size replaced by the relative roughness function, D sub S over R, the relative roughness function, R to the 1/3. Why is the 1/3 in there? That's kind of odd. The 1/3 is there is because of Manning. We got to blame Manning for this. Manning put the 1/3 in there. And we couldn't separate ourselves from that, because we can't go against Manning. Manning is one of the most established concepts in hydraulic engineering, even though it is not perfect. We believe that the Chesney equation is better than Manning. But who are we to straighten out 100 years of practice? Impossible. You can't do that. So we'll still have to accept that Manning is out there, and it's out there to stay for the foreseeable future. Okay, so the 1/3 is out there because of Manning, and we'll see later why. So the derivation follows. We're going to show that this, in fact, that this D of Lane should have been replaced by D sub S over R, which is dimensionless, because D sub S is the diameter, it's inches or millimeters, and R is the radius, the hydraulic radius. To the 1/3 does not affect the non-dimensionality of the process. So here we go. We have to talk about a friction function. We have to talk about the sediment transfer function, and we have to talk about a diameter function. which here at this point we call the Strickler relation. It'll be apparent later on while we get there, when we get there. By the way, this is straight algebra. We're not going to get into any differential equations over here. It is straight algebra. It should have been easy, but it wasn't. Okay, so, and I'm going to tell you later on why it took so long. Okay, the quadratic friction law, Ponce and Simons. Yes, in our paper, 1977 paper, we have the quadratic friction law over here, right in there. So from the beginning, we know the existence of this law. We did not, where is it? We did not develop this law. It was just hidden out there. Okay, not everybody uses it. I would say very few people use this equation, 10% maybe at most, the quadratic friction law. I'm talking about the common hydraulic engineers. I'm not talking about the scientists out there in a corner doing scientific studies. No, the common hydraulic engineers do not use this equation, okay? In which tau sub naught, bottom shear stress, rho density of water, F friction factor, and that's our friction factor, not Darcy-Weisbach. Darcy-Weisbach's is, ours is 1/8 of the Darcy-Weisbach. Now, those of you that, I believe it was in this class that I listed 6 or 7 friction equations, among them my own equation. Remember that? Yeah, remember that for the exam. Okay, the bottom shear stress in terms of hydraulic variables is, that's a standard formula. I believe I did talk about this at some time or some part, because this equation is part of basic hydraulics, basic open channel hydraulics. So if you did not take open channel hydraulics, which I suspect many of you didn't, then this equation will be new to you. Not new to you because I already talked about it, but I talk fast and you probably are just recognizing it by now. But you must know this equation. Without this equation, you cannot make any progress in sedimentation engineering, because all the sediment is due to traction, and this is attraction. This is the bottom shear stress, right? The stress attraction for the traction. Okay, so gamma unit weight of water, our hydraulic radius, we combine, and this is algebra in here. And I'm not going to over with you the details of algebra. I believe you're old enough that you can figure that out on your own. I do want you, I'm not going to go wait for you for 5 minutes to digest the equation. No, I'm not going to do that. I'm just going to go rather quick, because otherwise we won't finish. And then you can later on verify in the algebra and figure out that exactly I was right. So when we combine equation 3 and 4, we get this equation. The fruit number is chow. This is the definition of the fruit number. The fruit number is not defined in terms of the actual depth, but rather the hydraulic depth, D. That's the true definition of the fruit number. A lot of people miss there, but that's not the case. So the fruit number in chow. Chow is the Bible, excuse me for saying that, of open channel hydraulics. A book that was written in 1959 and that we still use. It's still used much as a reference, even though, let me be a little bit disrespectful here, a lot of people have not read it. They have it, but they have not read it. I know what I'm talking. They have not read it all. I may have read 3 chapters, 5 chapters, but Chow has 20 chapters. So when you combine equations 5 and 6, you get to equation 7. And then for hydraulically wide channel, in which because hydraulically wide channels is the first step in the analysis. That's where we're going to start. We later get to the hydraulic for the shape of the channel of any shape. The hydraulically wide channel, D is equal to R, or rather similar or very close to R, and therefore we get this equation, which I call very pompously, or without any humility, I call it the Ponce equation, the Professor Ponce friction equation. I developed this equation, I believe it was in the middle 70s, because I needed to do this, because I was doing hydraulics. So when you do hydraulics, you need to choose between Chesney or Manning. And researchers choose Chesney, maybe 10, 20%. Practitioners choose Manning 99.5%. But I was a researcher, so I decided to choose Chesney. But realized, being on this for a while, I realized that Chesney was how can I say, clumsy. That the better relation was a function of Chesney, which is F, which is RF. We defined RF. We found out that it was 1/8 of the Darcy-Weisbach, we said to ourselves, well, the Darcy Weisbach's over there, nobody's going to kill us for this. It's only 1/8, come on, you know? So that's what we did. This equation number 8 is our friction equation, which says that the slope, the friction, the dimensionless friction, the slope is dimensionless. The friction is dimensionless, F, and F has to also be dimensionless because we're talking here all dimensions. I mean dimensionless. So we get this equation. This equation is not only important, it's really fascinating because it ties the 3 very important things in hydraulics: the slope, the friction, and the Froude number, which is ubiquitous, meaning everywhere. You can find the Froude number everywhere because of its importance in this equation, or I guess you could say of its entry into this equation, which fundamentally ties friction and gravity. So then the question at this point may be asked, but friction and gravity are not the only forces. There's 2 other forces. You got inertia and you got the pressure gradient. And the answer is yes, but for the Froude number, they don't matter. They matter for some other situations, but not for this. And this is very important because it actually ties in the work that that was done by oh gosh, forgot his name right now. The gentleman that did a paper in 1982 where he said that that you couldn't get Froude numbers higher than 1. It was just not going to be there in a natural situation. And you know why? Because of this equation. Basically, when the slope goes up, the Froude number goes up, and the Froude number stays where it is. So that justifies Jared is his name. Those of you that are taking, sedimentation, this class, I have a tendency to get confused, one class with the other, what we say, the content. But this is a fundamental equation which I urge you to review for reasons that should be obvious by this time. Okay, the sediment transport function. General sediment transport function is, now where does this come from? This is the so-called Kolbe method. Who was Kolbe? Kolbe was a follower of Einstein. He was working for the Geological Service in the mid-50s. He pulled up Einstein's paper, he studied it, and he came up with a modified Einstein. The modified Einstein does not belong or was not developed by Einstein. It was developed by Kolbe. Then Kolbe subsequently developed his own method. Actually, he has 2 methods, which we are going to study later on. The Kolbe 1957, and then 7 years later, he got a little smarter and he developed the Kolbe 1964 method, which is considered as a standard for calculations that are common calculations. If you don't want to, I guess you could say shortcut. If you want to do a shortcut, Simons himself used to say that he always starts with the Kolbe 64 method because it's easy, it doesn't go anywhere, it's very well constrained, it's not crazy, it doesn't, I guess the Einstein method could go isolation, or rather you could say it could find itself in a corner, the Einstein method, but the Kolbe never will, because Kolbe made sure that wasn't going to happen. Einstein did not have the practitioners in mind. Excuse me for saying that, Professor Einstein, but Kolbe did. He had the practitioners in mind. He was working with the GS. Those people are practical. Okay, so according to Kolbe, this is the formula, 9, equation 9. But the M hasn't been defined. Well, the K1 hasn't been defined either. But the M is more important from the standpoint of the mechanism of transport. Okay, so Kolbe said that the M varied from 3 to 7. It was never lower than 3, and typically it would go up to 7 because he had to go somewhere. He measured it. He did a lot of measurements. It took him a while to get his methodology together, and he figured that the probable range for M was 3 to 7. 3 is a floor. You cannot have a 2.9 theoretically, but 7 is a very high number. 7, by the way. Why is a high number? Look at this equation. If the velocity is 2, and if you take it to the 3rd power, the value of the transport is 8, 2 to the 3rd power. Now take to the 7th power. What is the 7th power of 2? 2, 6, 8, 16, 32, 64. It's 128. So if the velocity is multiplied in here by 128 times, so it goes up very quickly because it's in the exponent. Does it go there? Yes, it does. Yes, it does. We know from the Colby method that that's the way it does. That kind of underpins the issue of the tremendous variability of the sediment transport that we find hard to pin down. Typically, the sediment transport will vary at least four, if not 5 orders of magnitude. Well, let's say, let me lower that down a little bit. At least 3, if not 4, but I've seen 5 too. Orders of magnitude. That means that it could be 1, it could be 10, it could be 100, it could be 1,000, it could be 10,000. So if you want to pin down a number between 1 and 10,000, you're out of luck. Because if you had 700, somebody else had 900, and you're 20% in error. But within the range that is possible, there's nothing. The error is very small. So it's relative, right? So this is the equation that we're going to use in here. It's a very common equation. It's got a Colby type method. Now the unit with discharge is 11. And the sediment concentration, that's also definition. Well, how do you define the sediment concentration? The discharge of sediment over the discharge of water with the gamma, because the gamma is to convert the water to sediment. Combining equations 10 and 12, then we get this equation. And then for hydraulically wide channel, we replace D for D, and then we find out with the Froude number. So lo and behold, our Froude number is always coming back. Here, the sediment concentration is a function of the famous K1 or infamous K1, because it's hard to pin down, but it is a number. It's a parameter, coefficient, times the Froude number. So the Froude number popped up again, but not in connection with the water, now in connection with the sediment. That's another equation that we developed early in the, if you want to call it a game, early in the game, we knew this equation 14 was there, okay? Combining these equations 8 and 14, now the algebra I'm going to leave to you because you got to review this on your own. We get concentration 15, or rather equation 15. The relationship between F and Manning, here we go. We cannot separate ourselves from Manning because people are going to eventually say, what about the Manning equation? What Manning equation value did you use? Or rather, what Manning value did you use? I don't think I had anybody ask me what Chesney value did you use, even though they're comparable. Manning is very popular, 98 to 1 or 99 to 1 that I can think of. So the Manning equation 16 is a tie between RF and the Manning, and we need to do that, right? In US customary units, we need to handle both US customary units and the in SI units. US customary is feet pound in the US usage, and a few countries in the world adopt or still uses the word, the US customary. The rest of the world uses the SI system, where SI stands for System International. It's a French word, French-derived word. Well, suffice it to say or to know that our friends, the French, invented the metric system or the SI system more than 200 years ago. And it is a good system, but unfortunately, it's not used throughout the world. So that's the story. In the US, we prefer, for whatever reason, we prefer our own system, which actually is not even our own, it's British. But the British, long time, maybe many, many years ago, I don't know when, they joined the SI system. Okay, so that's a long story on something that we already know. So in SI units, we have this. In SI units, the K2 is the 981, that's a gravitational acceleration in SI units. And in US customary units, we got to put the 1.486, which is the Manning constant, the change in the Manning constant. People say this, oh, I like the Manning equation because I can use either system and I don't have to use the coefficient. Correct. But you have to use two equations. The metric equation doesn't have a 1.486. And the Manning and the American system, meaning US customary, has the 1.486 in there, because otherwise, if you didn't put the 1.486, you got to change the Manning, and has not been done in the last 100 years of practice. So the preference has been change the equation, don't change the Manning. So it's kind of unusual, interesting. The stuff, it's all development, scientific development, of which neither you nor I have any control of, because it happened 100 years ago. The Strickler relation You guys probably never heard of Strickler. Who is Strickler? He was a German gentleman who studied the relationship between friction and grain size, grain size diameter. And we need to put him in here because if we don't, we won't be able to do it. So here you see, we came up with the friction, we came up with the sediment transport. Sediment transport was Colby. The friction, Professor Ponce. Excuse me for saying that again. But our equation, Colby's equation, and then Strickler's equation. With those three equations, we could come up with the final equation. So the Strickler said that the relationship between Manning's N, there's a typo in there, Manning's N and mean particle size is this, which is given, by the way, in Chow. This equation is listed or quoted in Chow, but he did it in US customary. So we needed to convert to SI units, and it can be converted. Any equation in some units can be converted to the other equation in the other units if you're careful. You got to be careful. Unit conversion is not easy. That's why it's preferable not to work with units, work dimensionless, and that's easy. Then you don't have to worry about if you made a mistake with the units or not. Okay, so we got in here D50 in US customary, 0.03442, which is, by the way, the number that I quote in my book. I checked it today. I wanted to see which one of these is the one in my book, the 0.342. So if you want to go look in chapter 5 of my open channel book, which is online, and you'll see this number, 0.342, which is referred to as a Strickler relation in feet. In feet. So that N is equal to this, and N2 is equal to that square. And when we combine equations 18 and 25, and I leave the algebra to you, then we get an expression for F, our friction factor, in terms of these coefficients, which very well known already, times the ratio ds over r to the 1/3. And where the 1/3 in there? Because right here, it came from 21. It came from 21. The 21 had already the 1/6 in there. So by the time we squared it, it got 1/3. So I told you already, blame the 1/3 on Manning, because that's the way he did it. Now, it bears because I do not believe all of you have heard this story, but where did Manning get the 1/3? And the answer is, he was an accountant. Go back and read the history. It's in my book, the historical reference. He was an accountant. He was doing hydraulics, because at the time in the middle 1850s, there were not too many engineers out there in Ireland. And they hired Manning and told him, you're going to do engineering. And he says, okay, fine. And that's what we call, I guess through the ranks or something like this. He didn't go to school like we do. Now you have to go to school. But at that time, 150, 180 years ago, people rose through the ranks or just got hired to do this work. And so Manning, over a period of 10, 20 years, he became very adept at hydraulics, which he did not study. And then when the time came to define the friction of the channel, he found himself looking at many equations. He collected 6 equations, which, by the way, are listed in Chow's book. And this story, I believe, is told by Chow in his book. And I also told it in my book. So he plotted 6 equations in one sheet of paper. And then, of course, they were different. The hydraulics is like that. They were all different. They all came up with different answers. So what did Manning do? He threw a line in the middle. And the line came up with the 1/3, actually 1/6. 1/6. So that's where the 1/6 originated, from a line that was the best fit to 6 equations that were pulled from here or from there. I'm not going to say anything wrong or bad about those 6 equations. All I'm going to say is that his methodology was a little bit haphazard. It was empirical. It was not theoretical. It was not theoretical. Well, Chesi was an engineer and he was doing theoretical work. So Chesi has more theory than Manning. Having said that, I mean, everybody knows that, and if they don't know it, it's because they've forgotten it, okay? The point is that we got the 1/3 in there. That's where we get the 1/3 in here. It'll be interesting for us to find out what would happen. What would happen, I'm telling you, because I know that if we use the Chesi equation, we wouldn't have the 1/3, but then people would not like our equation because we didn't use Manning, right? You got to be a little political about it. So we had to use Manning in here. So the sediment concentration, once you get all these equations, then you substitute equation 26 and 15, and you get this rather complex equation for the sediment, right? C sub S equal concentration, sediment, no, K1. K1 is the parameter, the basic parameter of this whole thing. S sub O over D sub S over R to the 1/3, and the K2, K1, K2, and K3 are the coefficients. The K1 is the essence of the sediment transport. K2 and K3 are related to the, K2 I believe is size, and K3 is friction. I'm pretty sure of that. So you got sediment, size, and friction. Those three independent from each other. Okay, they cannot be tied together because it's better to keep them separate. So now the concentration of sediments is this, algebra, just straight algebra. Therefore, and now we occupy, or rather develop, an equation which very much looks, it has all the parameters that Lane used in the right place. Only that Lane put in here a proportionality sign. Well, we're using equal because we didn't have to. We're stating the equality of these terms in here. So basically, long story made short, Lane was on the right field. Basically, he was very close, but he didn't do it. And why did he didn't do it? Because he was a practical man, field experience, but he didn't know all the equations that later on we learned through a lot of work and study. This equation goes back to 2011, and Lane's is 1955. So it was 56 years later that we put this equation together. Now, the modified Lane relation. The modified Lane relation is this one. No, that's the 31, the modified Lane relation. And our sediment transport relation is this. In SI units, we get 58.7 times this equation. In US customary units, lo and behold, we also get 58.7. So I spend a lot of time thinking about why 58.7. Because this number is a magic number. It shows up in English and in SI. SI in American US customary is the same number. So there must be some magic to this number that, to be honest with you, I don't know. I certainly, when I did this, I wasn't expecting for a number to show up in the front and yet be the same number in both systems. So that number must have some physics in there. Otherwise, it would show differently. We don't know. Okay, but it does work. So equations 34 and 35 are the same. The coefficients 58.7 and the sediment transport functions are independent of the system of units. There's something wrong in here. 34 and 36. Yeah, right. Yeah, basically it's okay. The sediment transport parameter is valid only for 3. Yeah, we use it for 3. Why 3? Why not 4, 5, or 6, or 7? Well, let's not forget that we were trying to get started. We weren't going to complicate the issue from the beginning, and then we would know where we go. So we use 3 because 3 is the one that gives us non-dimensionality. Why is 3 non-dimensional? Because people that have studied sediment transport, like Simons and many others, by the way, have realized that there's some relationship between the quantity of sediment transport and the so-called stream power, where the stream power is tau times velocity. And I already talked about this when we talked about Simons's paper. Simons's came up. Well, I don't think he came up, but he really emphasized or expounded, I guess is the word, on the stream power, on the concept of stream power. So what is stream power? Tau sub naught times V. But tau sub naught in itself is a function of V squared. So we would have to then definitely conclude that the stream power is a function of V cubed, which basically says that for very high sediment transport, the transport is going to be completely a function of the stream power. And we're going to have a chance to examine and explore what I just said extensively in the next half of the class. So if it's confusing at this point, so be it. So finally, we now figured out what the application should be. Let me finish it here. Sediment transport is valid only for 3. So for 4, 5, 6, or 7, one would have to determine it experimentally. Only one to be determined by calibration. Experience shows that this parameter varies typically in the range that K1 is 0.05 to 0.02. Applications. Now we're going to apply these equations, our equation, for a practical situation. So we say, assume pre and post development cases. Usually this is a development. An engineer is charged with figuring out, predicting what's going to happen after the structure is put together and built. It's on the ground. What's going to happen in a year, 2 years, 5 years, 10 years. So that's our job, to predict, so that society can evaluate the cost, the pluses and the minuses. At least that we know what's going to happen. So, which, by the way, this is interesting because I can show you many cases where this thing didn't happen, that the engineers didn't know what was going to happen. They went ahead and did it anyway because they were hired to do it, and then eventually it failed. A case in Tijuana, the 1993 flood on the Aguaje de la Tuna, of which I have already briefly talked about, but I will reiterate that later on. Okay, assume pre and post development conditions, then we're going to have A, which is the ratio of discharges, post over pre. B is the ratio of diameters. C is the ratio of hydraulic radiuses. You can see where we're headed. D is the ratio of discharges, water discharges, and E is the ratio of slopes. And when you put those three equations together and you take the ratios, you end up with equation 42. How simple could it get? Of which, once you know 4, you can find the 5th one. Don't attempt to know 3 and find the other 2 because it cannot happen. You have to have 4 and find the 5th one. So you have to question or ask yourself, what is going to be the slope? Mostly it's the slope that we're concerned with. So as an example, we have an example. We have 8.99. I tried to be as close to reality as I could here with the examples. 8.99, B equal 1, that means it didn't change. C 0.95, D 0.9, D is the one that is changing in here. D is the discharges, right? The discharge, water discharges is changing. The ratio of water discharges, 0.9, meaning development was 90% and pre-development 100%. And we get aggradation. And likewise, another example here, the same way, but in here, instead of putting D09, now we're going to put, instead of putting 8.99, now we're going to put 8.3, which is a substantial decrease in sediment discharge, 30%. It came down from post-development to pre-development, it came down to 30%. Because the sediment retention basin caught to 70% of the discharge. That's just a number to show the trend of the calculation of these equations. So when we do that, we get degradation. 0.34 is the calculation instead of 1.1, 1.12. 1.12 would mean steeper slope and therefore aggradation. 0.34, lower slope or smaller slope, therefore degradation. There's a caveat though, which everybody knows, everybody that's working sedimentation knows. If the bed of the river has gravel, the gravel would not be moved. And it would become, the bed would eventually become armored, which is kind of good, but you can't guarantee that'll happen because you can have a bed which is 100 feet deep with no gravel at all. You can also have a bed which is only 2 or 3 feet or meters deep, and then all of a sudden you find rock. And I've shown you examples of this in the issue of the Ojos Negros and many other places. So you always have to be wary as to where's the rock or where are the boulders, because the boulders are typically not going to be moved. And I'm going to finish in here with a story. I did a lot of work in the Ojos Negros Valley, and I've talked about in the other class, I've talked about the Ojos Negros Valley extensively. As a matter of fact, I think yesterday I gave them an assignment to read for the 7 people that are taking their class, of which 6 of them are taking this class, by the way. One day we went into this very remote area, and all of a sudden I found a piece of rock in the middle of the river, and the river was an ephemeral river, meaning typically there's no water. And this rock had a diameter, I'm not exaggerating, it would have been 10 to 15 feet. I didn't measure it. It was at least 10 feet, if not 15 feet diameter of the rock in the middle of the river. That is extremely unusual, by the way. That's a huge flood, like Noah's Ark flood, which happened a long time ago. It could have been 1,000 years. It could have been 100,000 years. We don't know, but it was a long time ago. So the question is, what is that rock doing there? And the answer is, of course, we know. It is resting. It's resting until the next Noah's Ark flood comes through, which may be 100,000 years or 1,000,000 years. We don't know, but it is resting. All of the rocks in the middle of the river that are big, too big for the current size, are there resting. And what would happen if another flood comes? They will come down, but they will disaggregate, they will break, they will deteriorate, rather degrade, so much that eventually you can't find them downstream. That example, that of course is something that I already talked about in sedimentation. The bed of the river, the grain size, the predominant grain size of a river bottom is much related to its slope. Meaning, if the slope is steep, the grain size is large. If the slope is mild, the grain size is small. So you go from cobbles to gravel to sand to silt, and there's no clay. I don't think anybody found clay in a river because the clay is too small and it will be carried directly into the ocean. And I say that because there's a lot of silt at the bottom of the deltaic situations. In deltas, you find silt at the bottom, but not clay. So with that, I'm going to stop. I actually exceeded my time. This has been an interesting class because there's a lot of numbers out there. I'm going to ask you to review the paper and try to find mistakes or errors. And if you do, please let me know. I don't think so. We've been reviewing this for 10 years. So at any rate, at this point, I am going to say goodbye.